Okay, so now let's go to our example, which is example 14.1 in the textbook. So let our function, which is f of x, is going to be like it equals to 1 for this interval from -1 to 1. Okay, so this is how the function is going to be like defined. It equals 1, like something like this, between -1 and 1. Okay, and after that it equals to 0. Okay, for the absolute value of x larger than 1, so it equals to 0 after that, for any value that is larger than 1, whether minus or positive, so it is something like this. For example, okay, we have like a jump here. Okay, certainly f is absolutely integrable, right? It's 1 and 0, we can integrate it, right? It's easy to integrate. So, and it's integrable, as we have said before. The Fourier series, or the Fourier integral coefficients of f are, so we are going to have our Fourier integral or coefficients as a omega, so we have a omega equals to 1 over pi, the integration from -L to L, cosine omega z dz, right? So it is from -L to L, or -1 to 1, right? This is a omega. You remember that? We have this is what, even or odd function? Exactly. If it's even function, it's from -1 to 1, then we're going to see this value, which is 2. Right? And then the integration of cosine is going to be sine. You're going to integrate this easily, and you're going to find that it equals to 2, or double sine omega over pi omega. Okay, this is a omega, which is going to be our first coefficient in the integral, right? Okay, so now let's go to the next coefficient, which is b omega. It equals to 1 over pi from -1 to 1 sine omega z dz. It must equal to what, without thinking too much? Exactly 0, because we have like odd function here, and it's from -1 to 1, so without thinking too much is going to be 0. So our coefficient here, b omega, is going to be 0, right? Okay, now let's go. As we said, this is a omega equal to 2 sine omega over pi omega, and b omega, it equals to 0, right? Okay, so the Fourier integral of f, remember that what we are doing, okay? We are trying to obtain Fourier integral for our function, which is going to be from 0 to infinity. This is the integral, and this integral is represented like this: a coefficient called a omega cosine omega x, plus another coefficient called b omega times sine omega x d omega. And remember this omega, it replaces what? Exactly, the summation index in the Fourier series is replaced with this integration variable omega. Okay, now we're going to look to this again. We're going to put it from 0 to infinity integration. A omega, we said that it equals to 2 sine omega over pi omega. This is actually a omega times cosine omega x d omega, right? First part here, the first term. And the second term is going to be exactly 0. It's going to be 0. So we are going to end up with this part only, right? Because f is what? Continuous. For any x that does not equal to 1 or -1, the integral converges to f of x, right? And this is right. This integral would converge to what? F of x. As we said before, we have like -1 plus 1 here, and we said that it equals something like this. So it is this function is going to have like it will converge, okay, to f of x, okay, for any value of x that does not equal to plus or -1. At x equal 1, which is this, if we say this is x-axis, for example, the integral converges to, okay, at 1 at this particular point here. As we said, this is our integration convergence or integral convergence or Fourier integral convergence theorem. Half f of x from right. Okay, f of x from right. What is the f of x from right? Okay, so this is at this point, okay, converging from right. It comes to what? It is, as you know, it is going to be 1. Okay, and then we are going to add to it f of x, okay, from left. From left, it equals to. Okay, so I think that here, this is because it is f of 1 from the right. I think that it is going to be, as we said before, this is like -1, this is +1, and the function is going to be something like this on the interval 1 to -1 to 1, and then it is going to be 0 after that. So from the right at 1, it is going to approach to 0, and from the left at 1, it is going to approach to 1, right? So this is supposedly to be, I think this should be 0, okay, and this should be like 1, 0 and 1. But anyway, it is going to be half at the end. So this should be like as I explained here. And also at -1, you're going to find it the same, okay? Whether that approaching from right, it is going to be 1, and approaching from left, it is going to be 0. So at also -1, it is going to be half. Okay, so as if that the Fourier series is going to like converge at half here and here. Okay, and here it is going to converge to the function itself. The function itself at 1, or converge to 1, of course, between -1 and 1. Okay, so this is half, where that the function is going to converge to. Similarly, the integral converges to half at x equal to -1, as I said here. This Fourier integral is a faithful representation of the function except at 1 and -1, where it averages the ends of the jump discontinuities there. And this is right, because it is, as we said, it is going to be faithful because it is going to be, yes, from -1, +1, it is going to be 1 here, and this is going to be something, for example, something like this. But when it comes at -1 and 1, it like average the whole. This is also the function here, so it average here at half here, similar here, and so on. Okay, so we are having like some average here. Okay, in view of this convergence, we can put it like this: 1 over pi from 0 to infinity, 2 sine omega over omega cosine omega x dw, which is already, this is what we have mentioned. This is the Fourier integral. Okay, it is going to converge. This is the convergence. Remember, we are talking about the convergence. What is the meaning of convergence? Means that what is the relation between the Fourier integral and the function? As we said here, the function is well defined. It is like 1 between 0 and 1, and it equals like 0 in other values. So this is a faithful representation of it. So it is going to be like, it equals to 1. This is the convergence now. Converge to 1, which is here between -1 and 1. For x between -1 and 1, right? Take care here. This is between -1 and 1 without equal. Why? Because at x equal to -1 or +1, what will happen? There is, yes, it averages. Make the average, as we said. It's getting the average between 0 and 1, so it is going to be half, right? So this is why it is half here. And for x, of course, absolute value of x larger than 1 means that to the right of 1 or to the left of -1, it is going to converge to what? 0. Exactly. Okay, so this is actually the whole story of this example. Okay, let's clean everything. So that's the end of it. And remember, as I said, that at the end we want to find the Fourier integral similar to what we said before for Fourier series for the function that we are dealing with. And we found that this is the integral that we're dealing with. This is the integration that is going to represent our original function. And then we tried to find what is the relation between the integral and the function itself, and we ended up with the convergence of the integral at the ends, okay, of the interval, and between the interval limits and outside of the interval limits, okay, outside of the interval limits. So we are talking here, as we said, about real line. Do you remember when I was talking about real line before? Okay, that is, we are talking about something that is, yes, real line. It's not an interval now from minus L to L only. Even that in our function, in our example, we were talking about from minus L to L, but still we are talking about the other remaining parts beyond the limits, okay? The other remaining parts beyond the limits. Okay, this is the integral, Fourier integral of this function. We understood very well through what we have learned from the theorem, and also from obtaining the coefficient of integral and ending up with our convergence theorem. Okay, thank you, and see you in the next video.